Hi, my name is Sammy Hasten, and I'm presenting the Lab 3 experiment of the magnetic field of a bar magnet. During this presentation, I'll be going over the purpose/introduction, the methods, the physics equations used, the values and graphical model, the computational model, the results, and then finishing with the conclusion. The purpose of this lab was to measure distance dependence of magnetic field due to a bar magnet, and as well as compare the experimental values to theoretical values from the Biot-Savart law. And a brief introduction to this lab. So lab 3 provides a model of the magnetic field due to the magnetic dipole from a bar magnet at various points. And then we use glow script code to compare the experimental and theoretical values to get a percent error. The methods really just use the Teslometer app as a magnetometer to measure magnetic field due to a permanent dipole magnet. And on the image to the right, the red X depicts the location of the magnetometer chip in the phone, which is in the upper left corner of my phone if you held it vertically. In the image, it's the top right corner. The first equation used was the Biot-Savart law for the magnetic field of the dipole. And this gets manipulated in order to solve for mu, which is the magnetic moment, towards the end of the presentation. The second equation shows the magnitude of the magnetic field for a bar magnet. The magnitude decreases as the observation location is moved further away from the bar magnet. The k in this equation is a combination of constants and parameters that are unchanged during the experiment, and it is important to note that the Earth also produces a magnetic field when trying to measure the magnetic field of the bar magnet. This slide shows the values and graphical models that I got from the Excel graph from the lab. If you look at the graph, you can see that the slope is actually the n value that we're looking for. So my n is negative 3.1198. And this is the observed value, but the expected value is negative 3, so I will go on to discuss that later in the lab of the percent error. Pictured on this slide is my computational model from the glow script code. The link to the code is in the bio of this video, but I didn't put it in the slides. The blue arrows in the computational model represent the magnetic field at on-axis locations. Next, the green arrows represent perpendicular observation locations. The yellow arrow at the top right of the image represents the off-axis location at 45 degrees. Printed to the right are just two of the values from my glow script code. Now I'll discuss the results from this lab. The experimental value was found to be negative 3.1, rounding to the first decimal place. The theoretical value is negative 3, so you can see there's a slight difference. And then I also calculated the magnetic moment calculation using this equation listed here. The equations are from previous slides, but I just manipulated it in order to find the mu, which was 3.9. And then the percent error equation is just the expected minus observed divided by the expected times 100. And when I calculated that, I got 3.33% error in this lab. To conclude lab 3, there's two questions I have to answer. If I hadn't oriented my experiment to compensate for magnetic north and instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field, then my graph would look the same, but the differences between the theoretical and experimental data would differ. The second question is, if I was to stick two identical magnets together end to end and run the experiment again, I would expect the measurements to be twice as large, but actually they would be unaffected by the addition of another identical magnet. That concludes my lab 3. Thank you, and let me know if you have any questions.